Hello everyone. I came across a new constant called Euler-Mascheroni constant. I thought of discussing it with you. Before that, I would like to introduce convergence of a sequence to a number. You say a sequence of numbers, which is of the form a1, a2, a3, so on up to infinity, converges to a number if it accumulates nearby the neighborhood of a number. So, neighborhood in the sense an open set. So, let's take a closer look. Suppose this is a real line and you are considering the following sequence. The sequence 1 by 2, 2 by 3, 3 by 4, 4 by 5 and so on approaches 1. As you go deep into the sequence, it goes arbitrarily close to the number 1. In order to say that it converges to a particular number, here it is 1, you must have infinitely many numbers inside this neighborhood. Infinitely many numbers of the sequence inside this neighborhood. Moreover, you should be able to give an index beyond which all the entries of this sequence or all the elements of this sequence shall belong to this neighborhood. The neighborhood can be arbitrarily small. A neighborhood means an open interval of the form 1 minus epsilon to 1 plus epsilon around 1. If you take any arbitrary number a, then a neighborhood around that would be a minus epsilon to a plus epsilon open interval. An epsilon can be arbitrarily small, but it is a positive number. It's greater than 0. You say that the sequence 1 over 2, 2 over 3, 3 over 4 and so on converges to 1 if you can give a value of index after which all the entries of the sequence belong to this particular neighborhood. Let's label the entries as a1, a2 and a3, so on. Any sequence shall come with this labeling because it is denoting the range defined by the sequence. In fact, sequence is a function. Any sequence is a function from natural number to the real number. Here we are considering only real sequences, so we will be pertinent to real numbers. A1 is the value of the function taken at natural number 1. A2 is the value of function A taken at natural number 2 and so on. And the index, by index I mean the input that you should provide for the function to give an output. So in the range description or in the range enumeration of this function, the location matches the index of the element. So if it's in the 5th position, then A5 is the index. Sorry, if it's in the 5th location, then 5 is its index. So if you can give me a value of capital N such that all the entries of this sequence with index greater than n belong to this neighborhood, then I say the sequence converges to 1. For example, here, if you take epsilon equal to 10 power minus 30, so here you have 1 minus 10 power minus 30 and here you have 1 plus 10 power minus 30 if epsilon equal 10 power minus 30. So this is equal to 1 minus 10 power minus 30. Now, if you take index really large, say you take the index to be 10 power 100, and what would be the functional value or the sequence corresponding to the index 10 power 100? It would be 10 power 100 by 1 plus 10 power 100. Now this is equal to 1 minus 1 by 1 plus 10 power 100, which is clearly greater than 1 minus 1 by 10 power 100, or it's greater than 1 minus 10 power minus 100. So you see, it's beyond 1 minus 10 power minus 30. It is really close to 1. 10 power minus 100 is really small and its distance from 1 would be too small when compared to the interval 1 minus epsilon to 1 plus epsilon that we consider. So this distance would be really far when compared to the distance from 1 to 1 minus 10 power minus 100. So it is inside this interval. Now if you take all the entries after this, the sequence being increasing, you will get it between this value and 1. As you could see, our general term is n by n plus 1, which is always less than 1. And it is also increasing because this part can be simplified as 1 minus 1 by n plus 1. And as you increase n, this value keeps on increasing. So this is when we say a sequence converges. Infinitely, you just need to have this in your mind, infinitely many values inside a given neighborhood. And moreover, if you should be able to give an index beyond which all the values of the sequence are present inside this neighborhood. So this is like accumulation of points near a particular point. And this is an example. When you say a sequence converges to a particular number, we also represent that fact by writing limit n tends to infinity a n equal that particular number, let's call k. So over here, the value of k is 1. So the limit argument and the convergence are just the same. Okay. Let's now consider the sum of 1 by 1 to 1 by n, which is known as the harmonic number. Now we have this value tending to infinity as n increases. Let's take another function, say Sn, which is ln of n. This is also the same as the log to the base e of n. Logarithm considered with base e, where base e is the Euler's number. Do not be confused with this and the Euler's constant we are going to study now. So this one also goes to infinity as n increases. Both of these are going to infinity as n increases. Now Euler did the following. He considered the difference between these two functions and analyzed maybe maybe that may not diverge to infinity. So let's call the difference function to be fn, which is hn minus sm. So that's like saying 1 plus 1 by 2 till 1 by n minus ln n. So the amazing fact here is both of these are sluggishly increasing functions. As you add numbers, the value is certainly increasing, and as n increases, this is also increasing. But they are slowly increasing. So their graphs shall look like this, something like this. As you increase the value of n, the rate at which they increase shall decay. So in that understanding, if you take the difference, then something really nice can happen. Maybe since both are damping as the increase is damping as they go towards infinity, their difference might be a constant, and that exactly is happening. The sequence fn is proved to converge to a constant gamma known as the Euler-Mascheroni constant. This result is proved that it converges to a constant. The value of that constant is 0.577 and so on. But the fact is, we do not know whether it is a rational number or irrational number. Neither we know whether it is transcendental or algebraic number. So algebraic numbers are just roots of some polynomial like this. So if you consider a root of this polynomial, then such numbers are algebraic, and transcendental numbers are numbers that are not algebraic. For example, pi is a transcendental number. So by the way, this polynomial must have integer coefficients. So if it cannot be expressed as a root of integer coefficient polynomial, then it's a transcendental number. Root 2 is an algebraic number because you can have x square minus 2 with a root being root 2. But till date, it's not known whether gamma is a rational number or irrational number. Neither we know whether it's algebraic or transcendental. That is really a mysterious number. Even a lot of great mathematicians have conjectured that it could be transcendental. So this one, transcendental. This one was conjectured by mathematician Conway, and in fact, Hilbert, great mathematician Hilbert, said that it's not an easy task to prove gamma is an irrational number. So such lot of mysterious things are hidden behind this constant. So I hope you find this interesting because it also involves some notion that we are aware of, which is convergence of a sequence. Hope you enjoyed. Meet you in the next video. Thank you everyone. Bye.